Hello, my name is Arnaud Trouvé. I'm a professor in the Department of Fire Protection Engineering at the University of Maryland. And the objective of this video is to provide an introduction to computer-based fire modeling. So let me get started with my slides. All right, this is the outline of my presentation. I will start with a brief review of fire dynamics, followed by a description of the landscape for fire modeling, followed by a description of the computational infrastructure that fire models are building upon, and finally, a few examples. All right, so fire is an uncontrolled combustion process, and this combustion process is typically characterized as a thermal feedback loop system. There is a strong coupling in fires between fuel sources that are typically in liquid or solid form and the gas phase phenomena where combustion takes place. Okay. In this feedback loop system, the fuel sources thermally degrade and provide flammable vapors that are the fuel for the combustion process. In return, combustion releases a large amount of heat, and a fraction of that heat will be supplied back to the fuel sources through convective or radiative heat transfer, and thereby provide the heat that is required by the thermal degradation of the fuel sources. So this thermal degradation process in fuel sources is called evaporation for liquids or pyrolysis for solids, and is typically endothermic, so it requires heat. So we see that in this coupled liquid solid phase and gas phase processes, the liquid and solid fuel sources are providing the fuel required by combustion, while combustion is providing the heat required by evaporation or pyrolysis. This is a loop, and it is easy to see that this looping process can self-amplify and become unstable, as is the case in a special event called flashover that corresponds to a rapid increase in the heat release rate for compartment fires. The main features of fire dynamics are given on the slide. They include the fuel mass loss rate in units of kilogram per second that corresponds to the mass of flammable vapors produced by evaporation or pyrolysis per unit time. The heat release rate of the fire in units of watt that corresponds to the rate of energy release by combustion processes, again per unit time. And the heat feedback generally measured by convective or radiative heat fluxes in units of watt per meter square that corresponds to the rate of energy transfer per unit surface area onto the fuel sources, again measured per unit surface area of a fuel source. All right, this is a rather brief introduction. Some of the main ingredients in fire dynamics are presented here. So first, the flow is buoyancy driven and is turbulent. And this flow aspect is important because it controls the mixing between the flammable vapors and surrounding air, and also the mixing of the combustion products with the surrounding gas environment of a fire. The combustion process is typically non-premixed and includes special difficulties, for instance, the possible development of flame extinction phenomena as occurs when the fire becomes underventilated, and because of oxygen starvation, it will experience partial or total quenching. It also includes processes like soot formation. Soot corresponds to carbon particles, primarily carbon particles that are going to have a dominant effect on radiation properties of the flame or the plume or smoke layer present in the vicinity of the fire. Thermal radiation is an important ingredient in fire dynamics because the heat transfer in the vicinity of the fire is typically dominated by radiation. And the heat feedback, for instance, tend to be dominated by radiation. In addition to this, radiation is also responsible for special events like flashover that I just mentioned a minute ago, And finally, pyrolysis, the thermal degradation of solid fuel sources, is an important problem that belongs to material science, and that basically controls the rate of formation of the fuel for the combustion process. So these are the main ingredients of fire dynamics. And this brief introduction here is provided so that we can appreciate that a fire model needs different tools to be able to describe that complex physics. In fact, it needs 3 different tools, 3 different components. The first component is the one that people will typically have in mind. It's a computational fluid dynamics component. It's a solver that is designed to describe the flow and combustion phenomena occurring in the gas phase. So this will provide a description of the heat release by combustion and heat transfer by convection. But in addition to this, as I pointed out, radiation is important. And radiation requires a special solver that describes heat transfer by electromagnetic waves. Okay, radiation energy is different than classical thermal energy, and the transport of heat by radiation requires a description of electromagnetic waves. And finally, in addition to the CFD and radiation solvers, we need a solid phase solver that will describe heat transfer by conduction and the possible thermal degradation associated with pyrolysis that takes place inside solids. So I would say that in contrast to the usual description of fire models as being CFD models, it's important to realize that there are more than that. A fire model is a CFD model combined with a radiation model and a solid phase pyrolysis model. Okay. Now, let me move on to a description of the landscape, the current landscape for fire modeling. And this will be pretty brief. So CFD, and you can see I'm going to adopt, emphasize the first component of a fire model here and using the CFD terminology, but again, bearing in mind that a fire model is more than just a CFD solver, it's also a radiation solver and a solid phase solver. But using the analogy to CFD models, a fire model typically decomposes the gaseous environment of the fire problem into computational cells, and each one of these computational cells will be described using statements of conservation of mass, momentum, energy, as given by continuum mechanics. So these statements are based on first principles of continuum mechanics and contain our best understanding of the physics relevant to flow and chemical reaction occurring in the gas phase. So this level of description, this CFD modeling approach for fire models is about 20 to 25 years old, corresponded to the development of models in Europe in the 1990s, followed by the development of models primarily in the US more recently. In particular, the fire dynamics simulator developed by the National Institute of Standards and Technology in the US, and Firefoam developed by FM Global in the US as well. These are the dominant fire models today. In particular, FDS is by large the #1 fire model used in the US and around the world by practicing engineers. The domain of application of CFD models is pretty wide now, primarily performance-based design, where CFD tools or fire models can be used to evaluate the performance of a building in the case of a fire scenario or fire event, in particular the compartment performance of the building, whether the fire is contained in a limited space, the performance, the evacuation performance, the people behavior performance, the performance of the smoke management system or the possible fire suppression system, and possibly as well the structural performance of the building in case of a fire. In addition to this, a lot of applications of CFD are directed towards forensic studies, the effort to reconstruct past fire accidents and to understand the mechanisms that led to the accident. And it's a tool that is widely used by researchers like myself to increase our understanding of fire behavior. Let me now spend some time describing the computational infrastructure associated with fire modeling. I'm going to focus primarily on the CFD component of a fire model. I will refer a little bit to radiation, and I will not refer to the solid phase pyrolysis model that is part of the fire modeling strategy. So bear with me on this. For the sake of time, I'm going to focus primarily on gas phase phenomena. The point I want to make in this slide is that it's important to realize that a fire model requires first a set of governing equations. So it requires a mathematical model on a piece of paper. Then it requires a numerical algorithm that takes the governing equations written on a sheet of paper and takes it to a computer so that this model can be simulated using computer power. And finally, it requires computer power to be able to run that simulation in a timely manner and in the most efficient way possible. So these are the three important components of a modeling exercise. It's not limited to fire modeling. It could be any computational model. You basically need to have some physics expertise, and that's where engineers work, develop a set of governing equations that represent the physics of interest. Then you need to have the help of an applied mathematician to be able to take these governing equations to the computer. And finally, you need the help of a computer scientist to be able to apply computer power to getting solutions of these governing equations and simulate the fire dynamics. So let me review the different components of this modeling strategy here in the next few slides. So here I have a set of governing equations based on the fundamental principles of continuum mechanics that express the evolution of the gas phase in the presence of flow and combustion. So you have here an equation for total mass, here an equation for chemical species mass, finally an equation for momentum conservation with an expression of the different forces that apply to a fluid system, and a conservation of energy statement, and the ideal gas law. Okay, all these equations are well known. They've been known for some time. The problem is that they correspond to a complex set of coupled governing partial differential equations, and these equations cannot be solved by hand, and we need the help of a computer to be able to simulate fire behavior. One question that I want to raise at this point is the question of spatial resolution. So what kind of spatial resolution do we need to solve the set of governing equations presented in the previous slide? There is also a similar question about temporal resolution, but I'm going to leave that question aside because temporal resolution is actually controlled by spatial resolution. So really the main question is the question of the spatial resolution of the simulation. To be able to illustrate my point here, I have 6 pictures of a map of Europe that are provided here with different spatial resolution, different number of pixels. And these pixels are the equivalent of a computational cell in a CFD framework. We can see that the last picture on the lower right here is the picture that is the most accurate, that uses the largest number of pixels. So that would be the level of resolution that we want if we want to emphasize accuracy. However, the higher number of pixels means longer computational times and a more expensive simulation. What I mean by computational cost here is already the time that it takes to get a solution on a computer. So the cost is time of execution. This most accurate picture here also corresponds to the largest computational cost. On the other hand, the first picture on the upper left here corresponds to a coarse resolution that may not be good enough in terms of providing enough accuracy to the simulation. However, that's certainly the simulation that would correspond. That's the level of resolution that would correspond to the fastest simulation because of the smallest number of pixels. So we can see that we have a trade-off in computational modeling between accuracy and computational cost. And that trade-off needs to be determined by the computational modeler and needs to be informed by an analysis of the characteristic landscape of the problem. So I want to move now towards a brief overview of the characteristic landscape of a problem that has a turbulent flow, that has a flame, and that has radiation. So here I present a classical picture of a turbulent flow that dates back to the 1970s. This is what is known as a shear layer or mixing layer. What you have here a flow from left to right, and what you have is a fast moving flow on the top of the picture that is going to start interacting with a slower moving flow on the bottom, downstream of a splitter plate that is on the left of the picture. And you have a mixing layer that develops an interface between these two flows that are developing parallel to each other, but because of the shear between the two streams, because of the fact that these two streams are at different flow velocities, the shear will create an unstable mixing layer that eventually will transition to a turbulent flow. So if I look at the right side of the picture here, the flow is turbulent, and I can see that I have large structures in this turbulent flow, large eddies that are responsible for the macro mixing that takes place in this mixing layer. And I have small eddies that corresponds to the micro mixing that takes place in this turbulent mixing layer, and that are responsible for the transformation of mechanical energy into heat. So the point of interest to me here from my discussion is that I can see that I have small eddies, and I can use turbulence theory to estimate the size of these smallest eddies present in a turbulent flow. And in the case of fire configuration, I can show that these smallest eddies have a typical size on the order of 0.1 to 1 millimeter. What about now the combustion process? The combustion process is going to bring additional length scales. In particular, a flame is known to be a very thin interface. And so a non-premix flame is a very thin interface between the fuel and the oxidizer. The oxidizer in our fire problems very often is the air. And so this thin interface is the region where the heat is released. And here I'm using a numerical simulation that was performed a few years ago by researchers at the University of Maryland in my group. And this thin interface has a characteristic thickness on the order of 1 millimeter for fire application. And finally, this review on length scale will be here completed by consideration of the radiation problem. So here I'm looking at a picture of a turbulent line burner that is on the order of 0.5 millimeter high. And I'm looking at, this is a methane flame, and the yellow luminosity from the flame corresponds to soot radiation. So you can see that we have a very intermittent structure of the emission from this flame, associated with the fact that the soot tends to accumulate in thin filaments that have a characteristic thickness, typically on the order of 1 millimeter. On the right-hand side, I have actually a laser diagnostic study of a similar flame along the wall. This study was performed in France a few years ago, and that also shows that the characteristic length scale, the characteristic thickness of the soot layers that dominate the radiation from the flame is on the order of 1 millimeter. So here, I can try to summarize this discussion. I can see I have a range of length scale for the flow. So I have large length scale, L sub T, these macro scales present in turbulent flow. I have small length scale with this characteristic size eta k. I I have the flame thickness, I have the thickness of the soot layer. All these length scales are relevant to the fire problem. They are important for the turbulent flow, for the combustion processes, or for the radiation emission processes. These length scales typically are on the order of 0.1 to 1 millimeter and require a DNS grid, require a grid resolution for direct numerical simulation, a brute force approach in which all these length scales will be resolved by the grid on the order of 0.1 millimeter. So this direct numerical simulation treatment of the problem is possible in academia at research for research level projects, but requires a 100 micron type of spatial resolution. This spatial resolution is way too small for engineering level projects, and something else has to be done. This something else corresponds to a strategy where the simulation will not resolve all the relevant length scale of the physics of the problem, but will be limited to resolving the large length scale, and we bring modeling for the small length scale. This approach is called large eddy simulation, LES. In this approach, the governing equations are filtered. They are kind of modified compared to the previous set of equations used in DNS. And the bar and tilde symbols here correspond to this filtering process. What this filtering process means is that it's only the large scale quantities that are resolved by a coarser grid that are going to be explicitly handled and treated by the governing equations. The small scales are going to be unresolved and are going to be described by models. So the terms here that are shown framed in red correspond to the terms that represent the effect of small scales. So these terms here correspond to convective transport by small scales of mass, momentum, and energy. This term corresponds to the combustion process that occurs at small scales. And these terms correspond to radiation transport, emission and absorption, and that also is controlled by small scales, not resolved by the grid. So all these terms will require modeling, and the LES simulation will be limited to a description, an explicit description of the large scale. So what this means is that now we have a nice formulation that can be performed with a coarser grid than the one that is required by DNS. We can use, typically in engineering projects using LES, we use grids that have a size that ranges from a centimeter scale to tens of centimeter scale. This is nice. The problem is that the level of accuracy of the simulation now is determined not only by the quality of the grid, but is also determined by the quality of the subgrid scale models that we've introduced to represent unresolved subgrid scale phenomena. So here again, to repeat a little bit myself, in DNS, we have this brute force approach that brings a lot of accuracy, but requires a very fine grid at the 0.1 millimeter level. In LES, we have an approach that can provide a variable level of accuracy, and it is consistent with practicing engineer computer capabilities. We only resolve the large length scale of a turbulent flow. We model the small length scales of turbulence, combustion, and radiation. And but it is at the expense of accuracy because we now rely on the quality of the subgrid scale models that are introduced in the governing equations. Now, another aspect I want to discuss is this aspect of going from a sheet of paper where we have the governing equations to the computer. So again, up to the previous slide, I'm assuming that I can write a set of governing equations, even in a large eddy simulation framework with nice subgrid scale models, and I'm going to assume that are accurate. But I'm still at the level of working on a sheet of paper. Now I need to go to the computer. This process of going to the computer requires the development of a numerical model, a numerical algorithm, and requires discretization. Computers don't work with mathematical objects like a continuous function f. Here I'm going to discuss the problem of developing a numerical algorithm in the context of a representative equation for an unknown quantity f that depends both on time and space. And to simplify, space will be defined, will be represented by a single dimension x. So f is a function of x and t, where x is a spatial coordinate, again, assuming one dimensionality, and t is time. And I'm going to assume that f is controlled by a governing equation that has an unsteady term, a convective term, and a diffusion term. This is a simplified equation for the sake of discussion. And of course, this is representative of the more complex set of governing equations that was discussed up to the previous slide. So discretization is a process by which we replace f of x and t, which is my mathematical object, by an array of values, by a set of discrete numbers that corresponds to the values taken by f at a discrete location xi and discrete times tn. So this is the discretization of space and time that is assumed in this process, and I'm replacing a continuous function by a set of values represented by the blue dots in this schematic. So the other aspect that I want to mention here is that a computer is very powerful in terms of speed, but a computer is very limited in terms of math. So a computer can do high school math, so it can do addition, subtraction, multiplication, and division. But a computer doesn't know what a partial derivative is. So partial derivative of f with respect to time, or the partial derivative of f with respect to space is unknown to a computer. So one thing that needs to take place when you develop a numerical algorithm is you have to translate your high-level mathematical equation here using high-level mathematical concepts into lower-level set of operations that can be interpreted and executed by the computer. So again, the computer can only do addition, subtraction, multiplication, and division. And so here you have an example of a discretized equation that is a model for the original governing equation for f that we had on a sheet of paper. But now this equation that we will written is an approximation of this original equation. And that approximation corresponds to a set of operations that can be executed by the computer and provide a numerical algorithm. If you look a little bit more carefully, you can see that this equation provides an evaluation of the value of f at location xi and time tn plus 1 as a function of the value of f at location xi or nearby location at the previous time step tn. So this provides a recurrent algorithm to evolve the solution from time tn to the next time tn plus 1. So this is a workable algorithm on a computer, and that provides a nice description of the physics and evolution of f due to convection and diffusion. The problem is that this simple scheme that I can derive as an engineer with a little bit of mathematical background will fail. And at some point, I need the help of an applied mathematician to be able to write a scheme that actually can work on a computer to solve this kind of problem. So let me illustrate this. So again, I'm considering my model equation, f as a function of x and t. I'm considering an arbitrary initial conditions. I'm specifying the condition of the test. I'm giving myself a convection velocity u and a specified value for the diffusion coefficient d. These values are just representative of what you may expect in practice. And here I'm plotting the exact solution. The black line corresponds to the initial condition, and the blue and the red and blue line correspond to the exact solution at t equal 5 seconds and t equal 10 seconds. So we see that the signal f, this initial f perturbation, is convected to the right by convection. It is also affected by diffusion. If I apply the numerical scheme that was presented 2 slides ago, then my simulation fails, and I want to explain what I mean by this. So the black dashed line that you can see in the background correspond to the exact solution. The red line and blue line correspond to the numerical solution, using the scheme that I had proposed at t equal 5 seconds and t equal 10 seconds. So I see that my numerical solution develops unphysical oscillations and that the amplitude of these oscillations grow in time. And in fact, the simulation will fail, the simulation will crash at some point, and I will not get, the simulation will stop. The fact that simple schemes fail and lead to unstable here, an unstable solution, it shows that you basically need the help from applied mathematics to be able to develop this correct and accurate numerical algorithm. So the scheme I shown here was the simple scheme you can try. It's a scheme that is called explicit in time and using central differentiation in space. In the 1970s, this problem was recognized, and there was a scheme called the upwind scheme that was developed as a solution to that problem. The upwind scheme here is shown. This scheme provides stability. Now we have a solution that is physically realistic but inaccurate. I can see that I have large errors in terms of predictions of the peak value of the solution. So this scheme is too dissipative and won't work. It is stable, which is nice compared to the previous scheme, but it's inaccurate and it is not an acceptable solution. And finally, today, thanks to applied mathematics, you have schemes that are much more elaborate. This is an example of the scheme adopted by FDS. This scheme is called the TVD scheme, using total variation diminishing approach, and this scheme is both stable and accurate. All right, so in addition to an algorithm, I need to have also a mesh generator that is going to help me design the computational grid that is required for my simulation. And here I'm just mentioning this in briefly by showing pictures of grids that are proposed for complex geometries. So you need, typically for complex geometries, you need to have mesh generators that conform to the complex solid surfaces and or complex geometries of the solid objects of interest for the fire scenario. By the way, FDS is limited to a simple rectangular shaped computational mesh, where, for example, a tool like Firefoam has a more flexible meshing capability ranging from structured to unstructured grids. All right, now once you have a numerical algorithm and you have a capability to generate a mesh, you need to be able to use computer power to solve to simulate your problem. Clearly, computational modeling has benefited from the tremendous increase in computer power thanks to the development of information technology since the 1970s. So we have now computer and network technologies that are widely available at a reasonable cost and a decreasing cost. And we are governed by what is known as Moore's law, which means that the speed of computers, doubles by a factor 2 every 18 to 24 months. And this trend is predicted to continue for the years to come. So we have more and more computer power, and we can more easily simulate complex engineering problems. This has led to the development of a number of a wide infrastructure, a number of computing platforms. They are ranging from the government labs or universities that have large-scale, massively parallel computing facilities with sometimes hundreds of thousands of processors. You have also smaller-scale computing facilities widely available in the private sector for engineering calculations. And you have also the development today of cloud computing, where you may not have to own your hardware. You can basically go on the web and basically use a cloud computing service and do the computation through the cloud that way. All these technologies have allowed the development of computational research for basic engineering sciences. So now, in addition to the classical approaches to science based on theory and experiments, now computational research is the third leg of science. And similarly, computational research has basically emerged as the tool of choice for engineering calculations. So engineers, practicing engineers routinely use computational models to be able to calculate the behavior of their engineering system. Let me take a few minutes to show some examples, and then we will stop there. I have a couple of examples coming from the academic world where I work. We are going to look at simulations performed with Firefoam, with a fine grade spatial resolution. What I mean by that is that the simulation, the first simulation, we have a spatial resolution of 4 millimeter. The next one, a simulation of 1 millimeter. So we're looking at basically research level projects that look at small system but with a high spatial resolution. The intent here is to improve our understanding of the fire physics. This first simulation, let me start the movie. This first simulation is looking at the simulation of a turbulent land fire that was studied experimentally at the University of Maryland a few years ago. Oops, sorry about that. So let me start again. This simulation is using a fine grid, 8 million grid cells, working on 256 processors and using 50,000 CPU hours. So the duration of that simulation was on the order of 2.5 days, using 256 computers, 256 processors on a parallel machine. This is the turbulent line burner is a turbulent line burner with, again, a 0.5 meter high flame, 0.5 meter wide flame. And this experiment was developed to study the transition to extinction of the flame. So this is a methane air flame. Well, no, I shouldn't say methane air. It's a methane air nitrogen flame. So you have methane injecting in the center of the system. And then you have in the co-flow, you have injected air with increasing amount of nitrogen. And when the amount of nitrogen present in the air nitrogen co-flow is too large, then the flame extinguishes because of oxygen starvation. So this correct simulation of this oxygen limit for extinction is a key to be able to describe extinction of an underventilated fire. The oxygen starvation process is the same. All right, so here, that was the purpose of this simulation, and the simulation correctly described the limit that was observed in the experiments of oxygen, a critical oxygen mole fraction of about 11 or 12% was the limit that led to the total flame extinction here, with a residual flame that is maintained by a pilot flame at the bottom. Let me go for a second example. This is an example that mimics, simulates an experiment from the University of Waterloo in Canada that was also recently studied at NIST. And these experiments correspond to a methanol air flame. The diameter of this liquid pool fire is 0.3 meter, and we are using millimeter scale resolution here in this particular simulation. This simulation is characterized by a strong puffing motion, and the goal of the simulation here was to check that we can correctly reproduce the puffing motion structure, and also the level of thermal feedback. So there were a number of measurements that performed at NIST of the radiative and convective heat fluxes back to the fuel surface. And we showed that we can reproduce the thermal feedback intensity in the simulation with an accuracy on the order of about 20%. And finally, my last example is an example let me go back. Is an example looking at FDS simulation. This is a more now a coarser level simulation that is closer to what a CFD engineer would do in the field. So it's a simulation that is more representative of practicing fire protection engineers. We are looking at smoke transport here in a commercial building. So our domain now is very large. We are looking at, we are looking at a building that is 40 meter deep, 50 meter wide, that has 5 story high, and is about 20 meter high. This is a commercial space, and we're representing the FDS geometry here, the central elevator shaft and the 4-corner stairwell present in the building. And we study this problem with different levels of leakage between the floors and the different spaces, the stairwell and the elevator shaft. We also look at different configuration for the doorways in that building. And we have a fire on the ground floor of that building and look at the smoke transport. And we are particularly interested in determining whether the smoke stays out of the stairwell or contaminates the stairwell. Clearly, our design aspect here is to make sure that the stairwell remains smoke-free for evacuation performance. So this simulation was performed using PyroSim as the preprocessor and also the post-processor of the simulation. And so what we're looking at here is first the black is the smoke that has invaded the ground floor. So we have a prescribed fire, a 10 megawatt fire on the ground floor. And we are interested in finding out whether there is smoke that contaminates the stairwell. Again, the ability of the smoke to move from one space to another depends on the pressure. So here, what we are already doing is checking the capability of FDS to correctly describe pressure effects in tall buildings. The pressure dynamics is complex and is determined by a combination of the stack effect in tall buildings combined with the overpressure brought by the heat release associated with a fire. It also depends on the ability of the model to correctly describe the flow through open vents and also through possible leakage pathways. We determined in this particular case that the smoke was not invading the stairwell. So this was a successful design simulation. Let me now finish here. So fire modeling has experienced a remarkable growth in the past 2 decades, and in particular driven by the development of fire dynamics simulator developed by NIST and the release of FDS as an open source freeware on the web. Fire models are today routinely used by engineers, and I would say that the bulk of fire protection engineering calculation is done by FDS today. So the days of doing hand calculations are kind of behind us. There are still a lot of issues associated with using FDS. And here, because I'm a fire researcher, I'm mentioning some of the hot topics in fire research. As far as fire modeling is concerned, there are still a lot of issues in developing pyrolysis models to develop the thermal degradation of solid fuel sources and the production of flammable vapors. There are also a few issues associated with the fact that our flow in fire scenarios, our flow is turbulent, but is typically featuring a moderate Reynolds number. So there are additional difficulties associated with this. Combustion processes exhibit flame extinction, as pointed out earlier, due to oxygen starvation, or flame extinction due to the activation of a fire suppression system. And extinction or reignition processes are difficult to describe numerically. There are issues associated with the small-scale physics that takes place when the flame is in a boundary layer close to a solid wall, like a vertical wall flame, for instance. That physics is not well described today in our fire models. There are huge problems associated with correctly describing soot formation in fire models, and soot is important for accurate radiation calculation. Also for radiation, one of the area of development that is currently happening is the development of radiation models with spectrally resolved properties, with properties that depends on the wavelength of the electromagnetic wave energy. The application of water sprays by sprinkler system or mist system can be modeled numerically in tools like FDS or Firefoam, but there are still physical challenges in terms of correctly describing the interactions with the combustion processes and the fire. And finally, we would like to be able to calculate not only the heat release rate of the fire, but also the composition of the smoke. And we would like, in particular, to calculate the toxicity of the smoke, the carbon monoxide content, the hydrogen cyanide content of the smoke, which is the main reason why people die in fire. But this is challenging, and it's still a work in progress now. All right, thank you for your patience. I went a few minutes longer than what I wanted to. Thank you for bearing with me. I'm going now to stop that video, and thank you very much again. All right, so... Hello, my name is Arnaud Trouvé. I'm a professor in the Department of Fire Protection Engineering at the University of... All right, so I'm trying to be back. Thank you for staying with me. This video was a little bit long. I hope it provided useful information. And now I would like to open the Q&A session.
All right, thank you, Dr. Trouvé. So we do have one question that was put in the chat to us by Dr. Sunderland. The question is, will DNS ever make LES obsolete? Will CFD ever make experiments obsolete?
So first, I don't think DNS will become an engineering tool for simulation. DNS is what we call a numerical experiment. It's an approach that has the greatest accuracy. We can use it computationally the same way people are performing experiments and explore the basic physics. But it is expensive, and even if in the future we have more computer power, we will probably apply the computer power by bringing more complexity to our engineering problems, bringing in more physics rather than increasing the resolution of the simulation. An additional aspect in that response is that in the end, the information provided by DNS is of great value to the researcher, and I'm one of them. I want to have that kind of detailed insight into all aspects of the physics, but it's too much for an engineer. There is no, when you calculate the response of an engineering system, there is no real need to know everything that happens at every particular location and every instant in your system. Typically, you're interested in some global aspect, so maybe some average, spatially average or temporally average aspect of your problem. So it is kind of this brute force approach of solving for everything is not the right approach. It's an academic approach. And then the second part of your question, Peter, is DNS or similar tools going to displace experiments? This has long been a discussion. I was in the early days of DNS being developed for combustion system in the early 90s, and there was a concern that maybe this was the end of the days of experimentalists. My experience is that this is not the case. There's a little bit of inertia, I must say. You know, if I look at the ratio of number of people doing experiments compared to the ratio of number of people doing simulations, we are still very much dominated by experimentalists, and sometimes it's not for the good reason. I think there should be more people doing computation and less people doing experiments. I think computation is somehow very often more productive than what some experimentalists can produce. So that's, of course, my biased comment and a little bit, food for thought, and I'm provoking there. So we are very far from being dominated by, in fluid mechanics or combustion or fire science, of being dominated by computational modelers. And so I think, when this question is raised, very often it's people who are trying to protect their turf, and they are protecting their turf very well, okay? In my career, since the 1990s, I've seen the development of computational modeling, and we are very far from having taken the field. But also, I'm a big believer in just combining the tools that we have. There are very often problems that are better handled by experimentalists, problems where we don't know what the physics is. I mean, a computational modeler needs to have some insight in the physics to be able to design correctly the grid and do some accurate simulation. Typically, we're not discoverers of the physics. The example in our department is Michael Gorner, who was studying this blue firewall, this blue world flame that has made the news in this past year. This phenomenon is typically a phenomenon can be discovered by experimentalists. That's not what computational models can do. So we need people to explore the physics experimentally, and then to be able to connect the dots and understand the details of that physics. I think then experimentalists should combine their tool with computational modelers. The last aspect of this question is that I want to add is that computational modeling, even at the level of DNS, I would say today, is still a qualitative tool. It's very hard to make this tool quantitative. So again, I mean, as computational modelers, we need experiments to give us the real numbers to check and validate our models. And on the other hand, I think experimentalists can only measure a few of the properties of interest, and whereas we can simulate all of them, and we can help together, we can connect the dots.
Wonderful. So we do have some questions that have come in through the Q&A function. The first one is the soot subgrid scale model based upon empirical data or the complete soot formation procedure? And is this including various species?
So the soot models that are used in fires typically are very crude. So they would be entirely empirically based. If you look at the default model in FDS, it's a soot yield. So it's one number describing the complexity of forming soot. The model is inaccurate, it is known, it's like a placeholder. But that model is completely empirically based, and we know actually it doesn't correspond to a correct description of soot formation. Now, in the combustion science community, there are more advanced models that have been developed. Usually these models are expensive. They are not necessarily very accurate, especially when you go from one fuel to another, then these models have to be recalibrated. And in addition to this, these models usually are based on a detailed chemical description of the combustion process itself, meaning we would have to look at the details of the formation of the combustion products prior to the gaseous products prior to looking at the formation of soot particles. And so these models basically are not the right approach for fire modeling, because we don't know what we're burning in a fire typically. So we are still, waiting for having a complete scientific understanding of soot formation, which is not the case today in the combustion science community. And then we need to be smart and be able to write models that are consistent with fire modeling applications. This entire field is completely open. I mean, right now, there is no good soot model available.
Great. The next question we have is, what is the difference between FDS and fire foam? Is there any difference in their results? For example, accuracy.
So let me just start that these models are developed by different teams, okay? And I think it's probably good to have some kind of healthy competition between different teams. I mean, CFD benefits from that in general. So FDS is developed by NIST and was released in year 2000 or 2001, and has enjoyed a great success. It's a tool that was primarily designed for practicing engineer applications. Firefoam was developed later at FM Global and was designed primarily for high-level engineering calculation, research-level engineering simulations. So the philosophy was a little bit different. Now, these two tools, when I compare them and compare the quality of their numerics, the numerical methods, the quality of their description of the physics, they are very comparable. And in fact, there are a number of benchmark problems that we are working on as a community within the context of the International Association of Fire Safety Science, IAFSS. And researchers working with FDS or working with FireFoam compare their results on some benchmark problems, like, for example, the methanol pool fire that I illustrated in my video. And basically, FDS and FireFoam provide similar results. One of the differences is speed of execution. FDS tends to run faster than FireFoam, which is an advantage for practicing engineers. One of the advantage of FireFoam, on the other hand, is that it has this more sophisticated meshing capability. So if you have to mesh, I don't know, a fire around a cylindrical tank, then you can actually respect the geometry, the cylindrical geometry of the cylinder in FireFoam, whereas FDS will have to develop to model the cylinder with rectangular blocks, like in a Lego land, and there will be some approximation associated with that. So there are a few features that are different, but these tools are very good tools, and they are equivalent in certainly in academic benchmark problems.
Okay, the next question we have is, how do we decide the number of species in any fire simulation?
So it depends on the objective. So the number one objective of a fire simulation is to calculate the heat release rate. When you are a training combustion, you're a combustion expert, you know that the number one quantity of interest in a combustion system is the rate of its release in units of watt. Okay, that drives everything. That drives the amount of smoke that is produced, the amount of heat that is released, the temperature of the smoke depends on it, and so forth. Everything depends on the heat release rate. So if you want to describe the heat release rate, we have simple models available that are based on a global combustion equation where you say fuel plus oxygen goes to CO2 and H2O. And basically describing the problem, the chemical problem at the level of fuel, oxygen, CO2 and H2O and nitrogen, 5 species, is enough to, in many circumstances, to describe the heat release rate. Now, if your objective is more ambitious and to calculate the carbon monoxide content of the smoke, or maybe tomorrow the soot formation, I had my doubts about the quality of the soot models, I expressed them, but tomorrow if we want to have a good soot model, maybe and probably we are going to need some more elaborate description of the chemistry. Some of the problems I work on, like flame extinction or flame ignition, then also require description of the chemistry, and therefore there is a little bit more chemical information that may be required. So for these problems, we're going to have to track more chemistry. But I would say that 95% of fire modeling applications I'm aware of today don't go there yet. Okay, that's the future. But right now we are focused on correctly describing the heat release rate and the thermal feedback to solid fuel sources.
Our next question is the challenge of modeling of complex solid fuel sources does it also include liquid fuels, for example, evaporation processes?
Yes. I mean, in compartment fires, typically we focus more on sources of fuels that are solid. But if you are looking at industrial fire safety, very often the fuel is liquid. And so, although the thermodynamics of evaporation is usually pretty well known, what's not easy is even when you have the correct level of thermal feedback back to a liquid source, a liquid container, you need to have typically an evaporation model that looks at how much of this heat coming from the gas phase is actually lost to the container walls. There may be a number of loss mechanisms. Experimentally, people have seen that actually the amount of evaporation that you get is less
than what you would get if you are looking at the level of thermal feedback and assuming an adiabatic system. So it is known that even if you have a simple laboratory scale liquid fuel pan, there is a significant amount of heat coming back from the gas phase for convective and radiative heat transfer to the liquid that will be lost to the container walls and through liquid motions and convective heat transfer in the liquid and maybe also some radiative heat transfer. This requires an evaporation model to be described correctly. So yes, there are some difficulties there, but I think it's primarily a thermal problem. And the thermodynamics aspect of it is pretty well known. The pyrolysis is not only a thermal problem, but the thermal degradation is the phase change that takes place in solid is not very well described chemically or thermodynamically, and so it is still a guess game. So the pyrolysis aspect of the problem is more complex.
Okay, this next question we have is a follow-up to something we answered earlier. The question is, if the soot modeling is crude in FDS, then can we say that the radiation modeling won't be very efficient in FDS?
That's a very good question. It turns out that we are a little bit lucky, I think. If you are looking at a fully developed fire, and so meaning a large-scale fire, and you have a lot of smoke in your room, then basically the emissivity of the smoke, the emissivity of the gas becomes 1, okay? And the radiation of the smoke is sigma temperature of the smoke to the power 4, okay? It's black body radiation. And you don't need to calculate accurately the emissivity. So that means that if you have a lot of soot, for example, in the smoke, and you are driven to that regime where you are optically thick and you are black body behavior of the smoke, then it's a matter of just calculating correctly the temperature of the smoke. Okay? And if you have the correct temperature of the smoke, you have the correct radiation influx everywhere. The difficult part is more in the transition from a small fire to a fully developed fire, in between, where you're going to transition from an optically thin problem to an optically thick problem. And then the emissivity depends on the soot volume fraction. And then our ability to correctly calculate the soot volume fraction is not there yet. So that's where we suffer. So we suffer in this transition regime where the fire starts small and grows. When the fire is fully developed, then we get a little bit lucky. As long as we have correct temperatures, we don't need to be very smart about the soot model. We don't need to have accurate values of the soot volume fraction. The only thing that matters is there are lots of soot, and then the smoke layer has an emissivity of close to 1. And the other details are not important anymore. So I think in many engineering applications, when you go to the fully developed phase of the fire, we get lucky that way.
Great. This next question is, this attendee is asking, is it possible to simulate the operation of concealed sprinklers using FDS?
I think the best thing that an expert can do is recognize that this is a little bit outside of their domain of expertise. I don't know that problem very well, and I've never worked on it personally, and I've never read about it. So FDS can simulate sprinklers, but I think you have to be careful. The simulation of sprinklers or water mist system, I think in the tools like FDS or Firefoam, is still something that is in beta mode. So it's available, it can be done. It hasn't been fully validated experimentally as it should. And so this is still something that has to be taken with caution. Now, when the sprinkler is concealed, I think it's a matter of bringing enough grid resolution to describe maybe the physics that takes place in this concealed space. But I don't see why not. I don't see why FDS would struggle with that if it has a good spatial resolution. But again, going back to my first note of caution, this is not a problem I know much about. So please bear with me on that.
Okay, so it looks like we don't have any other questions that are coming through. So I think this would be a good stopping point for this presentation. Thank you so much, Dr. Trouvé. That was an excellent presentation on your work in the field.